This is our second video on torque. The figure shows a 4-kilogram rod. All right, so there's the mass, and there's its length, 2.8 meters, and it's pinned at the left end, and its right end is free to move. The rod is released from rest in position 1, and the right end begins to fall, and it reaches positions 2, 3, and 4 in succession. In each of the 4 depictions, draw a dot showing where the rod's center of mass is. In the position 1 depiction, label this .com. .com, yeah, that's funny. All right, so the center of mass, if we're assuming this is a uniform rod, the center of mass is going to be right there for each of the cases. There's the center of mass. The net torque of the rod is generated by the rod's weight. Well, what's weight? Weight is m times g. So m is 4 and g, we're assuming we're on Earth, is 10. So that's going to be 40 newtons. And of course, that acts straight downward like that. Torque also depends on the effective lever arm, which is what for each depiction. All right, so let me draw the centers of mass in here again, right there. And the effective lever arm, the direction of it depends on which way the force goes, right? This force of gravity, which we just decided was 40 newtons, pulls straight down, doesn't it? Like that. So there's mg that I'm showing pulling down. So the effective lever arm is going to be at right angles to the force. Boom, right there. And boom, right there. And boom, right there. So the effective lever arm for position 1 is going to be half the length of the rod, which is going to be 1.4 meters. For position 2, let's see. Position 2, we have a 45, 45, 90 right triangle. And that means that if this length is 2.8, didn't we discuss that a 45, 45, 90 right triangle is basically a 5, 5, 7 right triangle. So the ratio would be the hypotenuse is a 7 and each of the legs is a 5. Well, if this hypotenuse is 2.8, then that means that these legs are 2. And if the legs are 2, then halfway over here is going to be 1. Position 2, the effective lever arm is going to be 1 meter. What about for position 3? The length between the pin and the center of mass, that length is 1.4. If this is a 60-degree angle, then I think it nicely turns out to be 1.4 cut in half, 0.7. All right, you check and make sure that we're good there, but I'm pretty sure we are. The lever arm for position 4 is 0. There's no perpendicular distance between that line of action of the force and the pin. So what's the net torque? Torque in general is lever arm multiplied by the force. In this case, the force of gravity, we decided just a little bit ago, was 40 newtons. So we're going to take each lever arm times 40. So 1.4 times 40 is 56. And what would the unit be? Newton meters. And it has a direction, and it's that way. For point 2, it's going to be 40 Newton meters, and it's going to go that way. For point 3, it's going to be 0.7 times 40. What's that, 28? Let me box these in so we know we got the right answers here. And what's the torque right there? Well, the lever arm is 0. So there's no torque when the rod is in its bottom position. One more point here before we finish this video. How will the rod's angular acceleration and angular speed vary between positions 1 and 4? The angular acceleration is going to decrease because the net torque is decreasing. We can see that in the numbers that we've just boxed in here. the torque is 56 to start with, and by the time the rod reaches the bottom, the torque is 0. So if the torque is decreasing, then the angular acceleration has to decrease, and here's why. Newton's second law says this: the net torque is equal to, again, we haven't talked about the moment of inertia yet, but we will, times the angular acceleration. So if the torque is decreasing, then the angular acceleration must be decreasing. So that's the first part of that. What about the second part, the angular speed? Well, the angular speed is going to continually increase. It's going to be rotating faster, faster, faster. Now, it's rotating faster and faster and faster at a lesser and lesser rate as it rotates. In other words, its angular speed changes quite a bit there at first. And then as it swings down, it's still increasing. It's still rotating faster and faster, but it's not rotating faster and faster at as great a rate. So omega, the angular velocity, will continually increase, and it reaches a maximum at the bottom. If this rod is allowed to swing through, then we're going to have a torque that will contribute an angular acceleration that has the opposite sign as the angular velocity, and then the pinned rod is going to start slowing down, which you know. If you ever did this, you know that when you let it go, it's going to slow down once it swings past the bottom.